Hi, we're Team Rexus from Nanyang Technological University, Singapore. Our team comprises of multidisciplinary students divided into chassis, drivetrain, batteries, communication, robotic arm, onboard lab, testing, and administration. This year's mission-based approach sees an improvement all across the board.
The 6 degree of freedom robotic arm has PID control at each joint that allows us to manipulate either a physical twin, a keyboard, or a joystick.
The rocker suspension improves traction and stability in rough terrain. It features a stainless steel core, a self-lubricating Teflon coating, and truss bearings, designed to withstand continuous use, making the rover reliable over long-term off-roading.
The robotic arm is equipped with a 1080 pixel camera and a 3D printed end effector providing real-time feedback with a robust gripping mechanism capable of lifting payloads of up to 6.2 kgs. This allows for easy manipulation of switches, knobs, buttons, keyboards, drawers, screws, USB ports, and joysticks with ease.
So the motion of the lab is achieved by the coordination of three lead-through assemblies, namely the X, Y, and Z axis. Each lead-through assembly is powered by a 12-volt stepper motor, and the motion is controlled on the linear rail. The coordination of three axes allows for agile three-dimensional movements. The whole system is controlled on an Arduino program.
The science subsystem is equipped with multiple sensors and instruments for detecting signs of extinct and extant life. Soil sample is collected using an auger and the solution is prepared. The filter is transferred to the cuvette trays using peristaltic pumps. The first cuvette contains BCA working reagent for protein detection, the second contains FDA dye for detecting enzymatic activity in live cells, and the final cuvette contains HERS 33342 for detecting nucleic acids. The result of these assays are confirmed by using the spectrophotometer manufactured in-house. Further, the lab also includes a microscope that can help us detect extinct life by revealing any microfossils if present. Finally, the rover has an array of sensors that include thermal sensors, NPK sensors, humidity sensors, UV sensors, and more to determine the viability of dig site before proceeding with sample collection.
For the wheels, we went with in-wheel motors to minimize potential points of failure. The tires were 3D printed TPU to allow compression for improved traction. Our steering performance was drastically improved when we matched the tire shoulder radius to a function of turning radius. We also took inspiration from construction vehicles for the treads to improve the performance of skid steering.
Our drivetrain system uses BLDC servo motors and drivers that can be toggled between position, velocity, and torque control. The drivetrain microcontroller enables skid steering by receiving teleoperation commands and actuates the motor in real time.
With these motors, the rover is capable of reaching around 15 km per hour and maximum torque of 16 Nm. Moreover, with maximum weight configuration, the rover can climb a 40-degree slope easily, which is an improvement from last year's tested 25-degree. SLAM is implemented using RTAP map with 2D LiDAR and RealSense RGBD camera, while path planning uses MoveBase with local obstacle avoidance.
Our autonomous system is fully integrated in the ROS framework. GNSS, IMU, and visual odometry are fused using extended Kalman filter for robust state estimation of the rover. Our core marker pulse detection is achieved using OGD RGBD camera and OpenCV library.
For our power distribution system, the PDN will distribute the power from 3 batteries to the M, the drive, and the laboratory system. Power is managed in this system using the DBDN and the IPDN. All these ports transmit telemetry wireless to the JSON, allowing us to diagnose any potential issues using the PCBs, voltmeter, and ammeter.
The rover communication system consists of a primary 2.4 GHz directional Yagi antenna that is mounted in the control station, which points towards the 12 dBi omnidirectional antenna of the rover. The secondary system consists of an independent 800 MHz antenna for critical systems, which is the mass camera and steering system. Headset-enabled system ensures almost negligible lag rover control up to approximately 1.4 kilometers. Finally, the tertiary system is a LoRa module that assists in enabling long-range recovery in case of communication loss.